So what is transfer function? That is your 1 into 1 upon s plus 1 upon 1 plus 1 upon s plus 1, right? So finally you will see 1 divided by s plus 2, right? So this is your s plus 2. Is it clear? So you are introducing a step change of 5 magnitude over here, right? Are you getting it in servo problem? So this one is a magnitude of 5. So can I write 5 upon s into 1 upon s plus 2? So I am not going to solve these things now. That it's a very simple thing. So that is 5 into 5 upon 2 into e to the power minus uh, that is s plus k. So that is equal to 2t. Sorry, that will be equals to 5 upon 2 into 1 minus e to the power minus what? T by tau. Tau will be equals to what? So that is equals to 2t. So at t tending to infinity, it will become 0. So that will be equals to 5 by t. So here your offset that is equals to 0 minus 5 by 2. That is equals to minus 5 by 2. Is it clear? So I hope these things is clear to all of you. Now I'll move forward for to understand the stability of closed loop. Since here we have seen that this is GC, this is your final control element. This is a process where U is there, that is load. Here your GP will be there, and this GP will give you output of Y, and here that GM will be there. Is it clear? And I'm just assuming there is a negative feedback system over here. Here that is XS, and here this one is YS. That is negative, that is positive. So we have seen that YS upon XS, that is GS, that is equals to GP, GC, GF divided by 1 plus GP, GC, GF, GM, right? This is your transfer function of this particular closed loop for the negative feedback system, right? So now the if the denominator of this one that is called as the characteristics equation, that is 1 plus GP, GC, GF, GM. Is it clear? So, to understand the stability of this particular closed loop, this characteristics equation becomes very important, right? How can I get characteristics of closed loop? Just I'll write the transfer function of this particular closed loop, and the denominator 1 plus GP, GC, GF, GM will be called as the characteristics of the closed loop transfer function, right? Characteristics equation of the closed loop transfer function. I hope these things is clear to all of you, right? Now, the value of GP, GC, GF, GM, the way it will be given in the problem, and you can understand the value of characteristics equations accordingly. Is it clear? So, first of all, the aim should be to write the characteristics equation, right? Once you can write the characteristics equation, now you can apply Routh-Hertz criteria for the stability analysis, right? So, I mean, if you try to understand the thing, in previous lecture, I told you if there is a transfer function GS is equal to 3 upon 5s plus 2 and 3s minus 1. So I told you there that you just go and try to check the poles. This is called as the poles of the transfer function. So here you will see poles is equals to 1 upon 3. Here see you will see poles is equals to minus 2 by 3. So if any of the roots of this characteristic equation is coming positive, then the system will becomes unstable, right? So this is also a characteristics equation over here. So the thing is that if I'll write the characteristics equations over here and I'll calculate the roots of this characteristic equation, right? So first aim is to write the CE, fine. Second, calculate the roots of characteristic equation, right? So if roots is positive, if roots is negative, if any of the root of the characteristic equation is positive, then the closed loop response is unstable. And if roots is negative, then closed loop response is stable. So when root is real, right now I'm talking about real root. When root is real, then first try to check whether it is positive and negative. If it is positive, if any of the root, if let's say, I'll tell you later on how you can check the roots. If any of the root is coming positive, then it will be your unstable system. But if all the roots are negative, if it is real, then the system will be a stable system, right? So let's say, so let's say this one is your transfer function over here, and here you can say 3 by s, let's say 2, and this one is this thing, and here you can say 3 by s plus 1, right? And this is a negative feedback control system over here. This one is your xs and this one is your ys, right? So first, how can I write the characteristics equation for this transfer function? Characteristic equation. So first I'll write transfer function. So transfer function is equals to your ys upon xs. So that is equals to 3 upon s into 2 multiplied with 3 upon s plus 1 divided by 1 plus 3 upon s multiplied with 2 multiplied with 3 upon s plus 1. Fine. So that is equals to 18 divided by s into s plus 1 plus 18. That is equals to 18 divided by s square plus s plus 18. Fine. So what is your characteristics equation over here? So the characteristics equation over here is s square plus s plus 18, right? So now I'll calculate the root of this particular characteristic equation. So s will be equals to minus 1 plus 1. Since this is a quadratic equation, so the roots can be calculated very easily. S is minus 1 plus minus 1 minus minus oh, that is 56 divided by 2. So that is equals to minus 1 plus minus root over 56i divided by 2. But here we are getting a complex root. But I'll discuss the complex root later on, right? So what can I do here is that is s square plus this one is 18. I mean the aim should be, if we are getting this characteristic equation, if the root is real, and if root is real, then you have to check whether it is positive or negative. If it is positive, any of the root is positive. Here you will get two roots. If any of the root is positive, then the system would be unstable. But if the roots, both of the roots are negative, then definitely the system will be stable. That's what the case is. I'll talk about the complex root or imaginary root later on. But let's say we are getting this kind of root, minus 1 plus minus root 56 upon 2, right? So there will be two cases, right? So your characteristic equation will be there, right? So having real roots and having imaginary roots, fine. So again, Real roots can be positive, can be negative. So if any one of the real root is positive, then system is your unstable. But if all roots of characteristic equation is negative, then the system is stable. Fine. Now imaginary root. So imaginary root is equals to real part plus imaginary part. Let's say a plus ib. So a is your real part, right? So the thing is that first you have to check the real part a, and again same things you have to apply, right? In the real part, if it is positive and if it is negative. If it is positive, then system is unstable, and if it is negative, then system is stable. I hope this thing is clear to all of you. Are you getting it? And one thing here can be, if it is zero, then system is marginally stable. Anyone has any doubt in this? It's very important. Every year you'll see some questions used to come on this particular topic. Again, this topic is very, very important and it carries huge marks. Okay, so if here you can see we have got this kind of root -1 plus minus root 56 I by 2. So again, my s was equals to -1 plus minus root over 56 I divided by 2. So the root is equals to -1 upon 2 plus root 56 by 2i and -1 upon 2 minus root 56 by y. So if I want to draw this on the complex plane, so this one is your real axis and this one is your imaginary axis, right? So this is your real part, right? Just try to understand. This one is your real part, minus half and minus half. So this one is your minus half real part. This one is your complex height, imaginary axis. So this is plus root 56 by 2. So root 56 is in between 7 to 8 and divided by 2. So this will be in between 3.5 to 4, let's say. So let's say this one is 4 and this one is 3.5, this one is 2. So it should be here. And again, it should be here. Let's say this one is 3.5 and this one is 4. So it should be here. So you can see over here. So your one root S1 is here and the second root S2 is here. But the real part is negative here. So that's why this particular system will be your stable system. Are you getting it? So since the root is here, that's why your first root S1 and second root, and the real part of this root is negative. That's why the system will be stable, right? So, but if real parts would be like that, plus 1 upon 2 plus root 56 by 2i and plus 1 upon 2 and minus root 56 divided by 2i. So, this would be here kind of thing. And if it is here, then this system is unstable. Is it clear? Fine. I hope this thing is clear to all of you. So this is the case. Now, next thing is that directly I am drawing a complex plane, right? This is your real axis. This is your imaginary axis, right? This is your first quadrant, second quadrant, third quadrant, and fourth quadrant, right? So the thing is that if roots are here, then this one is your unstable. If roots lies here, this one is your stable zone. If roots lies here, this one is your again stable, and if roots lies here, again it is unstable, right? So you have to check it, and you can apply the mathematics. This is your origin. So in the right of complex plane, this is your right. So you can draw observation if roots lie in the right of the complex plane, then the closed loop response will be unstable. Is it clear? Then the closed loop response will be unstable. And second one, if roots lie in the left side of complex plane, then the system will be stable, or that closed loop response will be stable. Is it clear? So this one is the case when, I mean, the thing is that if characteristics equation is like that, if characteristics equation is like that, 1 plus as square plus bs plus c is equals to 0. If this kind of equation is there, characteristic equation is there, then it is very easy to calculate the root. It is very easy to calculate the root, or you can calculate asq plus bs square plus cs plus d is equals to 0. I mean, for second order and third order, you can calculate the root, and you can understand by this particular method where the root lies, and we can tell this stability and instability of the system. But if the system is, let's say, as7 plus bs6 plus cs5 plus ds4 plus ESQ plus FS square plus GS plus H is equals to 0. So it will be very tedious to, calculate the root of this particular equation. It's not very easy to calculate the root. So again, you have to go to some another alternating method, so that you can analyze the stability of the system. And in frequently in a chemical engineering process, or in a process unit, you will see, you'll get these kind of roots for various processes, right? It's very higher order kind of quadratic equations you'll get, right? So to understand this kind of complexity, this is very complex equation, right? And here you cannot calculate the root. So to understand, to analyze, if characteristics equation is like that, right? So we'll use Raut test for, we will be using Raut criteria or RS test for the stability analysis of the system, right? So what I was telling, so the Raut test is here. I'll be writing. So the Raut test is a purely algebraic method, purely algebraic method for determining how many roots of the characteristics equation have positive real part. Fine. And Once we get to know that whether the root is positive or negative, or if it is complex, then how many roots of are having a positive real part, then we can understand the stability and instability of the system, right? So let's say if the characteristics equation is like that: a naught s to the power n plus a1 s to the power n minus 1 plus a2 s to the power n minus 2 plus a3 s to the power n minus 3 plus dot dot so and so forth, and we will go to n is equals to 0. This is the characteristic equation of a closed loop response right now you have got, right? So first m is should be all the coefficients should be positive. What RH criteria says, Routh criteria says, if all the coefficient, and what is all the coefficient? Coefficient is your A naught, A1, A2, so and so forth, AN. All this should be positive. If all these things are positive, then system will be stable. I mean, the system may be stable or may not be stable. Positive, then system may be stable or may not be stable if it is like that. But if any of the coefficient, let's say a naught, a1, an, is negative, then the system will be unstable, right? It's very important to understand these things, that first what you have to see in the RH criteria, you will see this particular equation. This is your characteristics equation, and that you will get it from your transfer function, right? The denominator of the transfer. You will see a naught, a1, a2, an. If all these are positive, then the system may be stable, may not be stable. But any of the, let's say a naught is negative, a naught is negative, then system will be certainly unstable. Are you getting it? System will be certainly unstable. So that's what the thing I am writing over here. This is your first case, and this is your second case of the characteristics equation over here, right? So this is very easy, that you will directly see the characteristics equation. Sorry, this one is very easy. You will see the characteristic equation, and if it is any coefficient is negative, then you will tell the system is unstable. But the crunching thing is in this particular thing here. If all the coefficient is positive, irrespective of that, system may be stable and system may not be stable. So to analyze these things, uh, um, R. Roth has given a array, and from there we can analyze that the system is stable or not, and how we can understand these things. Let's try to understand, right? It's very important. So first thing is that you have to write the characteristic equation from the transfer function. So that is your a naught s to the power n plus a1 s to the power n minus 1 plus a2 s to the power n minus 2 plus a3 s to the power n a3 s to the power n minus 3, and so and so forth up to an. Fine. So how can I make a Routh array? That's very important. So the Routh array can be made. I'll be writing here, that is your row, right? And this is your different columns, right? So in row I'll be writing, there may be a different kind of row. One first row, that is second row, third row, fourth row, fifth row, sixth row, and seventh row. But the question will be very small in the gate. So see, in the first row, what I'll see, that you have to write the alternate coefficient, that is a naught s to the power n, a naught s to the power n kind of thing, right? So let's say first, how you will be writing. First you will write the a naught. Again you will write a2, that is even, a4, a6, a8, and so on, so forth. Now here you will be writing odd one, a1, odd coefficient A2, sorry, A3, A5, A7 and A9, right? Now here you have to write that B1, I'm writing here, that is B1. I'll tell you how you can calculate B1, B2, B1, B2, B3, right? Here you can write C1, C2, C3. Here you can write E1, E2, right? Here you can write F1 and G1. This is the basic model of RH criteria, right? RH array. Now, since value of A naught, A2, A4, A6, A8 will be given in the problem, right? So these two will be given. The aim should be to calculate the value of B1 first. So how can I calculate the value of B1? B1 is equals to A1, A2 minus A naught, A3 divided by A1. Now you can see that is first I am multiplying this one, then I am multiplying this one and dividing this by this first element A1, right? That is A1, A2, A1, A2 minus A naught, A3, A naught, A3 divided by A1. I mean, it's a bit, you have to remember these things. There is no certain rule regarding that that you can remember. But if you will practice some questions, definitely you will remember these things. It's not very easy. First, you have to remember I'll multiply our multiplication will starts from A1, A2. That is higher minus A naught, A3, right? That's what the case is. So this one is otherwise if you will do multiplication opposite, let's say A naught A3 minus A1 A2, so you will do some mistakes. So don't do these things, but don't do any mistakes over here, right? Now once you calculated A B1, so now you have to calculate B2 because B2 is also unknown. How can I calculate B2? So for calculation of B2, you have to multiply A1 into A4, that A1 multiplied with A4 of the same next row multiplied with A naught into A5, A naught into A5 and divided by again A1. So I'll be writing B2 is equals to A1 A5 minus, sorry, A1 A4 minus A naught A5 divided by A1. And similarly, I'll be writing C1. C1 is equals to A1. Now here I have to calculate C1. Are you getting it? So C1, I'll be multiplying B1 A3. For C1, I'll be multiplying B1 A3 minus B2 A1, right? So I'll write B1, I'll change the color and after that is B1 A3, B1 A3 minus A1 B2 and that divided by your B1. And similarly, I can write C2, that C2 will be equals to B1 A5 minus B1 A5 minus A1 B3 divided by your B1. So that is equals to B1 A5 minus A1 B3 divided by your B1. Now, how can I calculate the value of E1? So if I want to calculate E1, E1 is equals to what? C1 B2 minus B1 C2 divided by C1. I can write E1 is equals to C1 B2 minus C2 B1. I'm repeating the same procedure. That's okay, same case. Again, I want to calculate E2. So the value of E2 will be C1 B3 minus B1 C3. So C1 B3 minus B1 C3 divided by your C1, right? So we have calculated the value of E1, E2. Now we can calculate the value of F1. F1 is equals to what? E1 C2 minus C1 E2 divided by E1. So I can write F1 is equals to E1 C2 minus C1 E2 divided by E1. Again, all these are very similar. It will go in the similar person. If it is nothing, so your G1 will be equals to what? That is equals to 0. Right? So we have calculated the value of all these coefficients B1, B2, B3. So now you can see we are having, I hope this thing is clear to all of you. I am just removing this. Fine. So once you will get this one. Now the thing is that so there is A note, A1, B1, C1, E1, F1. So you have to see this row, sorry, this column. This one is your column first, this one is your column second. Sorry, I'll write column second, third, so and so forth. So you have to see your column, all these column, first column, right? So the thing is that if this system has to be stable, right? If the characteristic equation is this, and we will make this RH root array, and if the A naught, A1, B1, all these things should be positive, then the system will be stable. That should be positive for a stable system. So the I can write here first the element of column first, that is A naught, A1, B1, C1, so and so forth, should be positive for system to be stable. Fine. Second one is if sum of the element in the first column are negative. If some of the elements in the first column are negative, then the number of roots, then number of roots with a positive real part is equals to number of sign change in the first column, and the system will be unstable. System will be unstable, obviously, because real roots are in the positive real part. What does it mean? So let's try to understand. I hope first point is clear. If any of the coefficient in first column is positive, then definitely the system will be unstable, or should be the element of the column 1, A naught, A1, A2 should be positive for the system to be stable. All these coefficients should be positive here. All these should be positive. Then it will be stable. But let's say you have made this particular column, right, by characteristic equation root 1, 2, 3, 4, 5. But here you have got, let's say, 3. Let's say here you got 7. Here you got minus 4. Here you got 3. 2. Here you got minus 3. Right? Sorry. In a problem, if you get this kind of coefficient in the first row, this one your column first, right? Here your column second, and so forth. But you see this one is positive, this one is positive, but this one is negative. So system will be your unstable. But now check, since this one is positive to negative and again negative to positive. So how much sign change is there? Positive to negative, so one sign change, again negative to positive, one sign change, right? And again positive to negative, so one sign change. So how many sign changes are there? So three sign changes. So if three sign changes are there, then there will be three roots having positive real part somewhere else here. Three roots will be there having positive real parts. Are you getting it? Anyone has any doubt? Tell me. Archana, any doubt? That is very important to understand. If it is clear, so you have to check the sign of all these elements. If sign is positive or negative, here you see that is first sign change, from this to this, again from this one was negative to positive, again positive to negative. So you can see there is there are three sign changes. So the number of sign changes will be equals to the number of roots having positive real part on the complex plane. If this one is your imaginary axis and if this one is your real axis, then we can understand three roots having positive real parts and the system will be unstable. Is it clear? So if it is clear, then I'll stop the class today because very less students are there today. Okay. So thank you all for attending the class. And in the next lecture, again, I'll be moving forward in this particular topic. Again, we'll do some problem on this particular topic, right? Okay. So thank you all for attending the class. You can leave now.